today I'm gonna talk about our recent study regarding the semantic formalization from the natural language specification for ARM. This is the joint work with my advisor, Professor Ogawa, also from JICE. So the aim of this research is to provide, to propose an approach to extract the formal semantic from natural language specification, which will enable the generation of the binary symbolic execution tools for various platforms, which are powerful to handle obfuscation techniques of malware, and it may help to correctly disassemble malware. So you may ask the question, what is the obfuscation techniques? Then let me give you an example. This is a piece of machine code, and if we disassemble this code, we can get the assembly code like this. But what is the problem? The problem is, here you can see an indirect jump that instead of jumping to a specific address, this jump will jump to an address stored in the register LR. So in that case, we have to apply the dynamic symbolic execution to explore the destination of indirect jump. So there are several approaches for binary symbolic execution. The first one is quite popular. This is, it will firstly transform the binary code to an intermediate assembly language like LLVM or VAX. The advantage of that approach is that it can easily support for multiple platforms. But the biggest drawback is that the coverage of symbolic execution actually depends on the disassembler tools like Capstone or IDA. The second approach is that we can add the path condition to an existing emulators. Then the drawback of this approach is that it has a limited interaction for handling indirect jumps. The third one is directly interpreting binaries like mark vector or BPAM. And the advantage of this approach is that it is really strong, powerful, and resistant with obfuscation techniques. But the biggest drawback is it requires a platform-wise implementation. So it becomes a really big problem if we want to extend our approach to many other platforms, because we have to implement it again. So, but the third approach is the most appropriate for malware analysis, because, as you know, it can be resistant with obfuscation technique. So, but the problem is there are very cheap architecture available right now. So it will take the third approach become more and more challenging. We focus on ARM that aiming to analyze IoT malware. In ARM, there are three main Cortex series: the Cortex M, Cortex A, and Cortex R, and each of them consists of a lot of instruction. That means we may need to pay a lot of human effort to prepare some formal semantics for task variation one by one. So we hope that we can propose a method to automatically generate such kind of semantics. So if so, it will become more easier for people when implementing the symbolic execution tools. So we ask the question, is reducing this tedious human effort feasible? And can we somehow mitigate the human effort on this kind of implementation. So fortunately, we observed some interesting point. The first one is that malware is mainly used most sequential programs. Then if we avoid multi-threads, weak memory models, and floating point arithmetic, we can consider binary has a simple semantic framework as transition on the environment made by register, memory, flags, and stack. And secondly, each instruction has a rigid language specification that is written in English. It includes the syntax, operation, and flag update. In x86 and MIPS, the operation also include the pseudocode, but for ARMS, the operation description is entirely written in English. That make our method become more and more challenging. So third one, various testing environments are available, like debugger and emulator. So after generating the code, we can verify the correctness by just comparing the environment after execution between our generated code with a trusted emulator. So here we have 3 observations. This suggested by the second one, we can use the operation and flag update section in the specification of each instruction and apply some natural language processing technique to formalize the semantic of this instruction. Then, suggested by the first one, we use a template-based programming to fill the extracted information to the template. Then the Java code will be generated. Then, suggested by the third observation, we can perform the conformance testing to test the generated method. So we answered the question in the previous slide that yeah, the binary form of semantic could be somehow systematically extracted. Note that we are not intending to provide a fully automatic method. We aim to reduce the human effort on the implementation of such tool. So we made 2 main contributions. The first one, we propose a new approach to extract the formal semantics of ARM instruction from its natural language specification. Then we utilize the extracted semantics to preliminary develop a dynamic symbolic execution tool for IoT malware analysis called Corona. And we also perform some preliminary experiments to verify the effectiveness of these generated tools. So let me give you an example of formal semantic extraction. How does it work? The left-hand side is a specification of the instruction UMAIL that collected from the instruction set in Cortex M7. Then here we have 5 pieces of information: the instruction name, the description, syntax, operation, and flag update. But we only use 3 ones: syntax, operation, and flag update for the extraction process. So as I was saying before, we use a template-based programming. So we introduced a Java template which has some missing holes that we need to fill the information from the left-hand side too. So this hole includes the instruction name, the arguments, a list of flags that need to be updated, and the operation description. So let's say, obviously, the instruction name and argument can be extracted from the syntax easily. For the operation extraction, we apply a sentence-wise extraction. So firstly, we will split all the description to to the separated sentence. Then we apply our method to each sentence one by one. For example, the first sentence can be interpreted as you can see, and the second one, the third one, the fourth one, and the final one. And also, we apply a similarity analysis method to detect which flag will be updated here. But how can we do that? Please move on. So here is the overview of the semantic extraction that includes two main tasks. The first one is operation interpretation, that we input the syntax, that we firstly normalize the syntax of each sentence. Then we use some NLP technique to interpret the operation. Then the second task is detecting the modified flag, that we applied a similarity analysis to detect which flag will be modified after execution. After finishing two tasks, we push the extracted information into a Java template, then the code is generated. After that, we verify the correctness of the generated code by performing a conformance testing. So for the operation interpretation, we observe an interesting point that there's many word phrase frequently appears among all the instruction. That suggests the possibility that we can use a rule-based approach to prepare the rules for the word phrase. Then once we have prepared the rules, we can use it for many times, and it will save a lot of human effort. So firstly, we do the parsing. We do the parsing, which will pass the input sentence into the syntax tree. Then we apply the word lemmatization and also removing unimportant word by calculating the TF-IDF score. Then we remove the unnecessary words. So in here, we solely consider the lowest level NP. NP stands for noun phrase. So the reason why we consider a noun phrase is that we have tried other kind of phrase like verb phrase or PP, but the result is worse. So we decided to use the noun phrase. So here we can extract the two noun phrases from this syntax tree. First one is to assign a 30-bit integer, and second one is first and second operand. The third one, multiply something in something, is the result of the whole sentence after replacing each noun phrase by a whole. So we have three patterns here. Then this pattern will act as the left-hand side of the interpretation rules. And note that these left-hand sides are automatically generated, extracted. So let's see how the syntax tree change after we remove all the unimportant word here. So we have three left-hand side rules, and we will start by the bottom-up manner from the bottom to the top of the tree. For the first phrase, we prepare the rules, the rewriting rules for the first noun phrase because it is matches with the left-hand side. Then next one, in is not matched with any left-hand side, and we keep it. Then do the same thing for the second noun phrase, and we got the right-hand side of the rules. And do the same thing, not match. When we merge it together, not much, then we keep it. Multiply, not much. Then we keep it, and we merge it together. And here, we match the third left-hand side. Then we prepare the rules for the left-hand side. The very important point here is that this rule can be reused in other interpretation. So in other interpretation, we may not need to prepare the rules again, and this rule can be used many times. That means once we have prepared it, we can use this for many times. So here is the generated statement. For detecting the modified flag, you can see here there's a lot of ways to describe the change of a flag. You can at the left-hand side, the descriptions in the left-hand side means that doesn't update any flags, and the description in the right-hand side means that we update some specific flags. Fortunately, this task is quite simple because we only need to give the answer yes or no. This flag is changed or not. So this can be regarded as a classification problem that can be solved by so many popular machine learning algorithms. And we decided to use the LDA model. LDA stands for latent delete allocation. This is a famous algorithm in text mining. Then after training the model, we put the target sentence through this model. This model aims to represent each sentence as a distribution of topics. So after pushing the target sentence through this model, we obtain a topic distribution of this sentence. We do the same thing, but for the model sentence. So what is the model sentence? The model sentence, we define, this is basically a sentence that carries a strong meaning of modified. So we, after representing this sentence as a distribution of topic, we can compare, we can measure the similarity between them, and if the score is lower than a threshold, we set it that modified, and otherwise it's unmodified. So we have collected over 1,000 of instruction over six ARM Cortex-M architectures. Then among them, we have generated approximately 700, and we have verified 662 extracted semantics. So how efficient is our method? We only need to, in our experiments, we only need to manually prepare 228 rules. That means approximately 0.34 rules to cover an instruction. Then we also need to prepare 35 primitive functions. Then the rules here are quite simple and reusable. And it took about 2 days of manual effort for the preparation. Then the algorithm will handle the rest. So yeah, of course, we have some failed case. We observe some case that causing the failure. The first one is the incorrect modified flag detection. In that case, as you can see over here, the description of the V flag is quite complex. This is, the V flag is left unmodified, and it is a quite complex synonym that, that our algorithm cannot handle at the moment. Then it will lead to a failure like this. The red one is the correct one, where we remove the V from the list of modified flag. And the second type of failures is the inappropriate sentences ordering in the operation section. And this is, you can see on the right-hand side, the correct order of the statement should be like this. That is because of our approach is a sentence-wise approach. So the generated code will be in the same order with the sentences in the description. So in case the description order is not correct, so the generated code is also not correct. So by utilizing the extracted semantics, we develop a preliminary version of a symbolic execution tools for ARM called Corona. And we make some experiments we conduct some experiment on the real-world IoT malware. And here's some example of that we show how Corona handle some jump destination. First one, Corona can be able to find the dead conditional branch here. By using dynamic symbolic execution, it can detect this branch is infeasible. Then it will not be reached when the program is executed. Corona is also able to find the destination of indirect jump. As you can see here, here is the indirect jump. Then in the left-hand side is the result that traces by Corona, where we explore the destination of this indirect jump, and it reflects the correct behavior of malware. Okay, so what else included in our paper? There's a lot of work done through our study. So we actually spend a lot of space in our paper explaining about other stuff, like how we select the appropriate instruction to process, and how we prepare the rules, and how we perform the conformance testing, and finally, the detailed design of Corona tunes. So if you guys are interested, I highly recommend you to take a look at the full text version of our paper. That will be available right now. So to conclude, in conclusion, we conclude that formal semantics of binary can be semi-automatically extracted by bridging natural language processing and machine learning and software engineering techniques. And to demonstrate this possibility, we propose a systematic method to extract the formal semantics of ARM Cortex-M from its natural language specification. Then we also generate a new dynamic symbolic execution tune, Corona, that specializes for IoT malware and performs some preliminary experiments. We are actively working on this direction, so we are planning to extend our methodology to other architectures and platforms like other Cortex series and MIPS. And we are also trying to optimize the generating symbolic constraint like loop invariant generation. So if you have any question or want to collaborate, just drop me an email. And thanks for your attention. I will be happy to take questions.